A big G times m divided by r squared, that's gravity. Okay, so what we're looking at here is our first electric potential example. And what we're being asked here is how much work is done in moving a 6.5 microcoulomb charge from ground to a potential 45 volts higher. So we can kind of think of any scenario to this, but the easiest way to think about it is with two parallel plates. And where we are starting with our 6.5 microcoulomb charge is here, the initial, and we're winding up over here, the final. Where this is at 0 volts, it is the ground. The ground we always think about as being at 0 volts. And on the left here, our final position, we're at some voltage 45 volts higher, so plus 45. Okay? Now, technically, we didn't actually have to make this 0 and 45. If we wanted to, we could have made this on the right 45 and the left as 90 and called this the ground, and this is just 45 volts higher than it. We could have picked any two numbers as long as our final position is 45 volts higher than our initial one. It's just easy to think about ground as being the 0, and then 45 working from that. And that's because whenever we take the delta here, remember the delta V is equal to the voltage drop, or the voltage change, the potential difference. That's always final minus initial. And it's much, much more easier here to think about 45 minus 0 than it is of thinking about, 135 minus 95. So that's just something to, or minus 90, something to think about there. So what we do have is we're going from here to here, just like that. And that is the case even though our electric field here, thinking about this as being the positive side and this as being the negative side, the electric field is actually pointing left to right with these uniform field lines that are perpendicular on each side. That's a field line right there. Field line, and don't forget we have slight edge effects, but we're going to ignore them because we're away from the edge. And all we're doing here is trying to figure out that work. And to do this, we can just think back to an equation we have. We can say that work is equal to negative QV, and remember that is a delta V technically, and we're actually good there, but I just want to show you that this QV is actually very similar. We could write it to negative Q, and then voltage, remember, we can think of that as being a distance you travel through an electric field, or some field, so this would be like E times R. Okay, so this right here, this E times R, is a voltage, but we actually, just for this problem, we are good of using this right here. So all we need to do is say that the work is going to equal the charge, which in this case is 6.5 microcoulombs, so times 10 to the minus 6. And then what is our voltage? What is the delta V? Well, that delta V, final minus initial, is 45 minus 0, so we're just going to get 45 volts off of that. And at that point, we just multiply these together. This here is coulombs, that's volts. And when we multiply them together, we're going to get negative, and I'll do a little bit of rounding here, 2.9 times 10 to the minus 4. Coulombs times volts is going to give us joules. And what we see here is that because we do have a negative answer, the negative 2.9 times 10 to the 4th joules, this work is being done against the electric field, which makes sense because when we were up here before looking at this, that charge was indeed being moved against the electric field, which means that some outside force had to be doing this. Okay, so that's our first little example there, nothing too bad. We'll do some more further on. But for right now, this is finished. Take it easy. Adios.